What if the most fundamental thing you know about reality, the thing so basic you have never once questioned it, is wrong? Not the speed of light, not the age of the universe, not dark matter, not dark energy, not the question of what existed before the Big Bang. Those are hard problems, but they are recognized as hard. Scientists have words for them. There are funded research programs. The field is actively working on them. This is different. What is being measured right now, in active laboratories, in peer-reviewed papers, in data that nobody is disputing, is that time itself is not behaving the way a century of physics assumed it would. Not at the edges, not in exotic theoretical scenarios, in measurements, in clocks, in the numbers that come back from experiments that were designed to do something else entirely and returned results that required a second look, and then a third, and then a formal paper asking what exactly is happening here. Here is the thing about a measurement problem. It is not a philosophical problem. Philosophy asks what time is in the abstract. Measurement asks what time does in the concrete, and then records the answer. When the answer comes back unexpected, that is not a matter of interpretation. That is a signal. And the signals are coming from multiple directions at once. Quantum physicists are finding that the collapse of quantum states, the moment when a fuzzy set of possibilities resolves into a single definite outcome, may be introducing a fundamental blur into time itself. Not metaphorically, as a measurable limit on how precisely any temporal interval can ever be pinned down. Research groups are producing results where particles spend negative amounts of time inside physical materials. That is not a rounding error. It is a reproducible outcome that quantum mechanics permits mathematically, and that our intuitions about cause and effect cannot absorb. Other researchers are asking whether time itself can exist in superposition. Not particles in superposition, not quantum fields in superposition. Time. The dimension, potentially in multiple states simultaneously. From a completely different direction, cosmologists studying dark energy, the force driving the universe's accelerating expansion, published findings in 2024 showing that dark energy is not behaving as the models predicted. It is evolving, which means the rate at which space-time is expanding is evolving, which means the structure of time at the largest scales in the universe is not the stable backdrop the standard model assumed it was. And then there are the fundamental constants, the speed of light, the fine structure constant, the gravitational constant. These are supposed to be fixed, not fixed in the sense of currently stable, fixed in the sense of invariant across the history of the universe. There is evidence suggesting they are not. Small variations, astrophysical signals, a natural nuclear reactor in Gabon that ran 1.8 billion years ago and left behind isotope ratios that let scientists test whether the constants were different then. The results are not conclusive. They are not nothing either. Now look at what you have. Quantum mechanics pointing at a limit on temporal precision. Experiments producing negative time values. Cosmology showing that space-time expansion is changing in unexpected ways. Evidence that the constants which define the laws of physics may themselves be slowly drifting. These are not connected research programs. They did not originate in the same labs or from the same theoretical frameworks. They are independent lines of inquiry that are converging on the same underlying problem. Something about our model of time is not complete. Here is my position on that. When a single anomaly appears, you investigate it and wait for more data. When anomalies appear simultaneously from quantum physics, from atomic clock experiments, from cosmology, and from the study of fundamental constants, the anomalies are no longer the story. The convergence is the story. What we are going to do here is follow the evidence. From the smallest scales, physics can probe all the way up to the structure of the universe itself. And by the end, the picture that emerges is not reassuring. It is not a thought experiment. It is not speculation dressed up as science. It is what the data says. And the closer we look, the harder it gets to explain what we are actually seeing. The most precise clock ever built sits in a lab at the National Institute of Standards and Technology in Colorado, and it will neither gain nor lose a single second over a period longer than the current age of the universe. Think about what that means. The universe is approximately 13.8 billion years old. This clock would still be accurate, not approximately accurate, not accurate within a comfortable margin. Accurate to 19 decimal places. That number is worth holding for a moment. Because 19 decimal places is not an engineering achievement. It is a threshold. At that level of precision, you are no longer simply measuring time. You are probing the structure of reality itself. And reality is starting to push back. Here is the thing about atomic clocks that most explanations skip over. They do not measure time in the abstract. There is no concept of time being directly captured by any instrument ever built. What an atomic clock actually measures is transitions. Specifically, the frequency at which an atom oscillates between two quantum energy states. Aluminum ions, cesium atoms, strontium lattices. Different clocks use different elements, but the principle is the same. The atom cycles between energy states at an extraordinarily consistent rate. Count the cycles. That count is your clock. The reliability comes from the fact that quantum energy levels are fixed properties of matter. An aluminum ion in Colorado cycles at the same frequency as an aluminum ion in Tokyo. That consistency is what makes the measurement meaningful. Why does the precision matter? Because once you can measure at this level, you can detect differences that were previously invisible. Not theoretical differences, measured ones. And the differences are there. Now look at what gravitational time dilation actually shows you. This is not speculative physics. Einstein predicted it in 1915. We have verified it repeatedly and with increasing precision. The finding is this. Clocks in stronger gravitational fields tick slower than clocks in weaker ones. Put a clock on the floor and a clock on a shelf 1 meter above it. Run them. Compare. The clock on the shelf ticks faster. The difference at that scale is around 1 part in 10 to the 17th, far too small for earlier instruments to detect. Modern optical lattice clocks measure it over a vertical separation of 5 centimeters, not kilometers, 5 centimeters. What does that tell you? It tells you that time is not uniform across space. The rate at which time passes depends on where you are in a gravitational field. Closer to a massive object, time moves slower. Farther away, it moves faster. This is not a quirk. It is not a measurement artifact. It is a physical property of the universe that has been confirmed in lab conditions, in GPS satellite corrections, in astronomical observations, and in a 2024 White House memo formally acknowledging that the moon's clocks tick faster than Earth's clocks because the moon sits in a weaker gravitational field. That memo exists because we are planning infrastructure on the moon, and the time difference is large enough to matter operationally. Roughly 58.7 microseconds per day faster. Small in daily terms. Significant over months. Significant enough that communications and navigation systems will need to account for it. Here is my position on what this actually means. Most treatments of gravitational time dilation present it as a curiosity, a relativistic correction, something that applies to GPS satellites and exotic astrophysics, but leaves ordinary life untouched. That framing is technically defensible and conceptually misleading. Because what the measurement establishes is not a correction to time. It establishes that time itself is a local property. Different locations in a gravitational field are not moving through the same time. Not moving through it at different rates, relative to some master clock ticking in the background. There is no background. Time, as far as any measurement can tell, is what clocks read. And what clocks read depends on where they are. Consider the Earth's core. The core sits deep inside the planet, subject to significantly stronger gravitational pressure than the surface. By the same physics that makes the shelf clock run faster than the floor clock, the core runs slower than the surface. Over the 4.5 billion years of Earth's existence, that difference accumulates. The Earth's core is, in measurable physical terms, approximately 2.5 years younger than its surface. The same planet. 2.5 years of difference, not because something unusual happened at the core, because that is what gravity does to time when you let it run long enough. Before you can understand the deeper problem this creates, you need one more piece. GPS satellites orbit at roughly 20,000 kilometers above the surface. At that altitude, gravity is weaker. Their clocks run faster than ground-based clocks, by about 45 microseconds per day due to the gravitational effect alone, partially offset by a slower rate from their orbital velocity. Without continuous correction for both effects, GPS positioning errors would accumulate at roughly 10 kilometers per day. Every phone navigation system on Earth depends on engineers accounting for the fact that time passes at different rates in different places. This is not theoretical infrastructure. It is operational fact. So here is where this lands. We have instruments precise enough to measure time differences over 5 centimeters of vertical distance. We have confirmed that the planet's core and surface are aging at different rates. We have built a global navigation system that only functions because we continuously correct for the curvature of time across altitude. And the most precise clock ever constructed is now sensitive enough to detect variations we do not yet have complete theoretical explanations for. The clock has outpaced the model, which means the question is not whether time varies from place to place. We have measured that it does, but whether it varies in ways we have not yet accounted for. Here is the problem that nobody in popular science talks about clearly enough. We have 2 theories, 2 frameworks, both tested to extraordinary precision, both confirmed by experiment after experiment across more than a century of accumulated work. General relativity describes gravity, space-time, the large-scale structure of the universe. Quantum mechanics describes the subatomic level, particles, fields, the behavior of matter and energy at the smallest scales we can probe. Each one works. Each one predicts outcomes that match measurement with almost absurd accuracy, and they are fundamentally incompatible. Not slightly in tension, not in need of minor adjustment. Incompatible in a way that physicists have known about for decades and have not resolved. The place where they break against each other most sharply, the place where the contradiction is clearest and most uncomfortable, is time. Here is the thing about general relativity. In Einstein's framework, time is not a fixed backdrop. It is a dimension, a physical thing. It bends, it stretches, it curves in response to mass and energy, exactly the way space does. You saw that in the previous section. A clock near a massive object runs slower than a clock far from it. That is not a clock malfunction. That is time itself running at a different rate. The geometry of space-time is what time is. It is dynamic, local, part of the fabric of physical reality, and that fabric can be shaped by what sits inside it. And now, look at what quantum mechanics says about time. Nothing. That is the answer. Quantum mechanics treats time as a fixed external parameter. In every quantum equation, time simply exists as the backdrop against which quantum events occur. You do not apply quantum rules to time itself. You do not ask what the quantum state of time is. It is a stage, invariant, universal, running at a constant rate while quantum systems evolve within it. That description and the description from general relativity are not reconcilable. One says time is a dynamic physical dimension shaped by mass and energy. The other uses time as a fixed, unchanging parameter and does not ask where it comes from or what it consists of. These are not two perspectives on the same thing. They are two mutually exclusive claims about what time fundamentally is. Why does this matter beyond theoretical physics? Because both frameworks are applied constantly. GPS satellites require relativistic corrections to keep their clocks synchronized with clocks on the ground. That is general relativity in engineering. Semiconductor transistors, lasers, the machines in medical imaging, all operate on quantum mechanical principles. Both frameworks run the modern world simultaneously. And at the boundary, where you would need them both to apply at once, the mathematics breaks down. The equations produce infinities, no physical meaning, no resolution. And the thing sitting at that fault line, the quantity both theories have to address, and neither can describe in compatible terms, is time. Here is my position on that. This is not a technical gap waiting to be closed by a better calculation. It is a signal. When two extraordinarily successful theories produce irreconcilable descriptions of something as basic as time, the correct response is not to treat it as a bookkeeping problem that future math will sort out. It is to ask whether our underlying concept of time is incomplete. Recent research has begun pushing into that question from a direction that most coverage ignores. Quantum collapse. Here is what that means. In quantum mechanics, a particle does not have a definite position, a definite spin, a definite energy until something forces it to resolve. It exists as a superposition of possibilities. Measurement collapses that superposition into one outcome. For most of the history of quantum mechanics, physicists treated collapse as a mathematical rule rather than a physical event. What actually happens during collapse, mechanistically, has been called the measurement problem, and it has been deferred more than it has been answered. New theoretical work proposes that collapse is a real physical process, and that it may be connected to gravity. The idea is this: gravity is what causes quantum superpositions to resolve into definite outcomes. The larger the mass difference between the possible states of a system, the faster the collapse. A particle stays quantum because the gravitational distinction between its possible states is negligible. A chair does not stay quantum because that distinction is enormous. If this is correct, it carries a direct consequence for time. Because collapse events do not unfold on a perfectly smooth temporal background. They happen in curved spacetime. And curved spacetime means there is a limit, a fundamental one, to how precisely you can specify when something happens. Not a limit from instrument error, not a limit from engineering. A limit written into the physical structure of reality itself. Below some minimum timescale, the question of when an event occurred stops having a precise answer. The act of resolving a quantum possibility and the geometry of time at that scale are entangled in a way that introduces irreducible uncertainty into any temporal measurement. What this connects to is something physicists call the Planck time, roughly 10 to the power of negative 43 seconds, the scale at which quantum gravitational effects become dominant, and every current theory breaks down completely. Below that threshold, time as we understand it may not exist in any meaningful sense. No before and after, no sequence, no duration. The concept loses its referent. What we experience as time may be something that emerges from a deeper structure, the way temperature emerges from the statistical motion of molecules, real and measurable at our scale, not fundamental at the scale beneath it. And here is the question that follows from all of this. If time is emergent, if it is shaped by mass, if quantum collapse introduces a hard limit to how precisely any temporal measurement can ever be made, and if the two best theories we have produced descriptions that cannot both be right about what time is, then what exactly are we measuring when we measure time? That is not a rhetorical question. It is an open one. The field has not answered it. We have two complete, tested, extraordinarily successful theories of how the universe works, and they cannot both be right about what time is. Every equation in fundamental physics works the same way run forward as it does run backward, not approximately, not with minor corrections, exactly the same. Take any process described by quantum mechanics. Reverse the direction of time in the equation, and the mathematics still holds. Do the same with general relativity. Do it with electromagnetism. The equations do not care which way time is moving. They are indifferent to the distinction we consider the most basic fact about existence. And yet, ice does not unmelt. Smoke does not return to the wood. A dropped glass does not reassemble from its shards and rise back to the table. You have never seen a fire unburn. You have never watched a ripple on water contract back to a single point. Every physical process you have ever observed moves in one direction, and that direction never reverses. Here is the question that should stop you cold. If the laws governing every particle in that glass, in that fire, in that spreading ripple say nothing about which direction time moves, why does the process always go one way? This is not a new problem. Physicists have known about it for well over a century. It has a name: the arrow of time. It refers to the observable, consistent, universal directionality of physical processes in a universe whose fundamental laws do not contain that directionality. The gap between those two things has never been fully closed. What we have instead is a standard explanation, and it is worth examining carefully, because the standard explanation has a structural problem that most treatments of this subject skip past. The standard explanation runs like this. The second law of thermodynamics says that entropy, roughly disorder, always increases in a closed system. A broken glass has more disorder than an intact one. Dispersed smoke has more disorder than concentrated smoke. Time appears to move forward because entropy moves forward. Systems evolve from lower entropy to higher entropy, and we experience that directionality as the passage of time. This is not wrong. The entropy argument is real, and it does explain a great deal. But here is the thing about it that the textbook version leaves out. The second law of thermodynamics is itself statistical. It does not say entropy must increase because of some deep law. It says entropy increases because higher entropy states are vastly more probable than lower entropy ones. There are so many more ways for a system to be disordered than ordered that disorder is almost certain to win. Almost. Not guaranteed. Statistically overwhelming, but not fundamental. Which means the arrow of time under the standard explanation is not a bedrock feature of reality. It is a probability argument, a very powerful one, but a probability argument nonetheless. Now, look at what researchers at the University of Surrey published in recent work on open quantum systems. Open quantum systems are systems that interact with their environment. They exchange energy, they are not isolated. Virtually everything in the real world qualifies. Their research examined the mathematical structure governing how these systems evolve over time, and specifically what happens to the reversibility of time within that structure. What they found was a factor they called the memory kernel. The mathematics of how these systems evolve retained a formal reversibility. The equations preserved the property that time could theoretically run in either direction, even in systems that are exchanging energy with their surroundings, even in conditions that look, at our scale, completely irreversible. Reversibility was not destroyed by the interaction with the environment. It was still there, embedded in the mathematics, hidden but present. What does that actually tell you? It tells you that whatever produces the directionality of time we observe is not coming from the fundamental equations. It is emerging from something else. Emerging is the operative word here, and it carries a specific technical meaning in physics that matters. When physicists say a property is emergent, they mean it is a feature of large-scale, many-particle systems that does not exist at the level of the individual components. Temperature is emergent. A single atom does not have a temperature. Pressure is emergent. One molecule bouncing around does not exert pressure. These properties appear only when you have enough particles interacting that statistical patterns dominate. The individual parts do not carry the property. The collective behavior produces it. Here is my position on what the Surrey research implies. If temporal direction is emergent in this sense, then the arrow of time is a feature of systems large enough for statistics to overwhelm the underlying reversibility. At the scale of atoms, of quantum events, of individual particle interactions, the directionality we experience does not exist. Time has no preferred direction at those scales. It is only when you aggregate enough particles, enough interactions, enough complexity that the arrow appears. Not because any law requires it, because the numbers make it statistically dominant. Why is that disturbing? Because it means the one-way time we experience is not a fact about time. It is a fact about our scale. We are large enough and warm enough and made of enough interacting parts that the statistical arrow dominates completely in everything we observe. But nothing in the underlying physics requires it. The laws themselves permit reversal. The reversal just becomes extraordinarily improbable at scales we can observe, which is not the same thing as impossible and is not the same thing as forbidden. And here is the question that follows from that. If the direction of time is statistical and emergent rather than fundamental, what does that say about the nature of time itself? We do not usually say temperature is a fundamental property of reality. We say it is a useful description of aggregate behavior. If the directionality of time belongs in the same category, then the structure we are actually dealing with when we talk about past and future, cause and effect, is a large-scale approximation sitting on top of a physics that does not contain it. The asymmetry of time, the bedrock fact that yesterday is gone and tomorrow has not happened yet, may be something the universe does at large scales without it being written into any of the laws governing what happens at small ones. The standard institutional response to this pattern is careful and consistent. These effects exist only at quantum scales. The macroscopic world we inhabit is not affected. Causality is preserved at every level that matters for the physics of daily experience. This is technically accurate. A photon spending negative time in a rubidium cloud does not make your morning run backward. The large-scale arrow of time remains intact. These are real and valid points, but here is the question worth sitting with. Why are we so confident the weirdness stays contained? The macroscopic world is built from quantum components. Every atom in every structure, every interaction in every biological process, every signal in every measurement device, all of it operates at the quantum level underneath. We observe classical behavior at large scales because quantum effects average out statistically across enormous numbers of particles. That averaging is real, but averaging does not mean the underlying weirdness disappears. It means we are not currently measuring it at the scales we live at. The question is whether we are failing to detect it, or whether it genuinely does not propagate upward. And frankly, we simply do not possess a complete theoretical account of exactly where the quantum world ends and the classical world begins. That boundary, the so-called measurement problem, is one of the deepest unsolved questions in physics. We are confident the weirdness stays contained partly because we have not seen it escape. That is a different thing from understanding why it does not. Quantum superposition is the property that lets a particle be in two places at once, or spin in two directions simultaneously until you measure it. Most people have heard this described in terms of Schrödinger's cat. A cat is sealed in a box with a mechanism that may or may not have triggered. Until you open the box, the cat is neither alive nor dead. It exists in both states at once. The measurement resolves the ambiguity. Before measurement, both outcomes are real and coexisting. That is not a metaphor. That is the actual mathematical structure of quantum mechanics, tested and confirmed across a century of experiments. Here is the question that almost nobody asks next. What about the clock in the box? If the cat is in superposition, if the event that kills or saves the cat has not resolved into a single outcome, then the moment at which that event happened has also not resolved. The clock inside the box, measuring when the trigger fired, when the vial broke, when the outcome became definite, that clock is also suspended. Which means the time at which the event occurred is not fixed. It is also in superposition. Two possible times coexisting, neither one more real than the other, until something outside the system forces a resolution. This is not a rhetorical extension of the thought experiment. Physicists are beginning to treat it as a serious technical problem. Here is the thing about superposition that gets lost in popular explanations. It is not that we simply do not know which state something is in. It is that the question of which state it is in does not have a definite answer. The particle is not secretly in one place while we remain ignorant. Both states are physically real and simultaneously present. The mathematics requires this. Experiments confirm this. When you extend that logic to time, when you ask whether a temporal interval, not just a particle, can exist in this condition, you are not doing philosophy. You are following the equations where they lead. Now look at what the experiments are actually proposing. The most advanced optical atomic clocks in existence measure time by counting transitions between energy states in individual atoms. The NIST aluminum ion clock achieves an uncertainty of around 19 decimal places. This is the most precise measurement humans have ever made of anything. And physicists are now asking whether a clock this precise could be placed into a physical configuration where it measures itself ticking at two different rates simultaneously. Not one rate while we look away, not two clocks running at different rates. One clock, one system, two tick rates, both physically present at the same time. Why is that physically possible to even propose? Because the tick rate of a clock depends on its position in a gravitational field. We covered this. Clocks lower in a gravitational field run slower. That is not a mechanical effect. That is time itself passing at a different rate. So if a clock is placed in a quantum superposition of two different heights, which is physically achievable, particles can be in superposition of location, then the rate at which time passes for that clock is also in superposition. The clock is ticking at two different rates. Both are real. Neither has resolved. What does that mean for the concept of a moment? A single defined instant in time. If the clock can tick at two rates simultaneously, there is no single answer to what time it is reading right now. There is a superposition of readings, a superposition of nows, each valid, each physically real, coexisting until some interaction with the environment forces the system to resolve into one. This is where the argument stops being about quantum weirdness in isolated systems and starts being about the structure of time itself. Fast. Massive in implication. Before you can understand what confirmation of this would mean, you need to sit with what it would actually remove. Every intuition you have about the present moment rests on the assumption that now is singular, that there is one current state of reality, one configuration of the universe that is actual, while the past is gone and the future has not arrived. Superposition of time does not modify that picture around the edges. It removes the foundation it stands on, not mythology, not speculation, the actual structure of the mathematics followed to its conclusion. The standard response from physicists is careful. These are quantum systems. They decohere extremely rapidly when they interact with their environment. The superposition collapses almost instantly into a single resolved state. The macroscopic world we live in never shows us this directly, and that is technically accurate. But here is my position on that response. Decoherence describes how quickly superposition resolves. It does not explain why the resolution produces a single, definite time rather than some weighted average. It does not explain what is happening physically during the interval before resolution. And it does not address what it means that the most fundamental description of reality permits multiple time states to coexist at all. The fact that the window closes fast does not mean nothing happened while it was open. The institutions are publishing this work carefully and correctly. Proposed experiments are real. The theoretical frameworks are being developed in peer-reviewed physics journals, not on the fringe. What is not happening is any serious public reckoning with what it means if the experiments confirm the hypothesis. If time itself can be in superposition, then the question, what time is it right now, may not have a single answer, and the act of asking it may be what forces the universe to pick one. In 1937, Paul Dirac, one of the founders of quantum mechanics, a man who was not given to speculation, published a paper suggesting that the fundamental constants of physics might not be constant. Here is the thing about that claim. Dirac was not writing philosophy. He was doing mathematics. He noticed that when you compare certain large numbers in physics, the age of the universe, the ratio of electromagnetic to gravitational force between a proton and an electron, you get values that are extraordinarily close to each other. Too close, he thought, to be coincidence. His interpretation was direct. These numbers track each other because they are connected. And if they are connected, and the universe is aging, then they must be changing together as it does, not randomly, proportionally. The gravitational constant in Dirac's model weakens as the universe grows older. What does that tell you? It tells you that the rules of physics are not set in stone. They are set in time. Now look at what the word constant actually means in physics. The fine structure constant governs how strongly charged particles interact through electromagnetism. It determines the structure of atoms, the behavior of light, the chemistry of every molecule in existence. The speed of light determines causality itself, how fast any signal can travel, how fast any cause can reach any effect. The gravitational constant determines how matter curves space, and how that curvature produces what we experience as time. These are not adjustable parameters. They are the bedrock numbers, the ones that go into every equation in physics as fixed inputs. Change them and you do not get a different physics, you get a different universe. Dirac's hypothesis sat in the literature, taken seriously enough to test, controversial enough that nobody quite knew what to do with it. Then, in the 1970s, scientists got a test case they had not expected. In the country of Gabon, in West Central Africa, there is a uranium deposit called Oklo. About 1.8 billion years ago, the conditions in that deposit crossed a threshold. The uranium was concentrated enough, the water content right, the geometry correct. A self-sustaining nuclear chain reaction started underground, ran for hundreds of thousands of years, and then stopped. A natural nuclear reactor, the only confirmed one ever found. Why does this matter for the constants? Because nuclear reactions are extraordinarily sensitive to the exact values of the fundamental constants. The rate at which neutrons are captured, the specific isotope ratios that result, all of it depends on the fine structure constant and related values being precisely what they are. If those constants had different values 1.8 billion years ago, the Oklo reactor would have produced different isotope ratios than it did. So scientists measured the isotope ratios in the rock. They compared what they found to what the known constants predict. The match is close, very close, which means the fine structure constant has not changed substantially in 1.8 billion years. But here is where it gets precise. Close is not the same as identical. The Oklo data PLR says a limit on how much the constant could have varied. It does not prove zero variation. It proves the variation, if any, was smaller than the instrument could detect. And there are astrophysical measurements pointing in a direction the Oklo data cannot rule out. When astronomers look at light from extremely distant quasars, objects so far away that the light reaching us left before Earth existed. They can measure how that light interacted with gas clouds along the way. The specific wavelengths absorbed depend on atomic physics, which depends on the fine structure constant. Some measurements have suggested the constant at those distances, that far back in time, was slightly different from its value today. Not dramatically. The variation would be in the 5th or 6th decimal place. But present. Several independent research teams have found this signal. Others have not. The debate is active. Before you can understand why string theory is relevant here, you need to understand one thing. String theory does not predict that the constants are fixed. It predicts the opposite. In string theory, the constants we measure are not fundamental numbers hardwired into reality. They are the values that the extra dimensions of the theory happen to settle into when the universe cooled after the Big Bang. Different settling, different constants. And if those settling points can shift slowly over cosmological time, then the constants we measure today are moving targets, not anchors. String theory does not tell you how fast they move, but it does not forbid movement. In several string-based models, the fine structure constant and the gravitational constant are expected to drift slowly over the lifetime of the universe. This is my take on it. When the most speculative framework in physics, and the oldest uranium deposit on Earth, and the light from billion-year-old quasars all point toward the same open question, the straightforward truth is that we simply cannot determine whether the constants are constant, not completely. And the field responds with precision and caution, which is correct scientifically. But what it does not do is sit with the implication long enough to say what that implication actually is. The implication is this. If the constants are changing, then the laws of physics are changing. Not metaphorically, literally. The gravitational constant determines how time dilates near mass. The fine structure constant determines the structure of the atoms those clocks are built from. Every measurement of time we have ever made depends on constants that may be slowly drifting, which means the second we defined yesterday is not identical to the second operating a billion years ago. Not because our clocks were imprecise, because the physical reality the second is defined against was different. Time, not our measurement of time, but the physical phenomenon our measurements are tracking, was governed by slightly different rules, and will be again. If the constants are changing, then the rules governing what time is and how it flows are different now than they were when the universe began, and different now than they will be when the universe ends. 68% of the universe is made of something that no instrument has ever directly detected, that no theory has fully explained, and that is currently stretching the fabric of spacetime at a rate that is apparently not what we thought it was. That is not a rhetorical setup. That is the current state of cosmology. The thing being described has a name: dark energy. It accounts for roughly 68% of the total energy content of the universe. Dark matter accounts for another 27%. Everything else, every star, every planet, every atom, every instrument ever built to study any of it, adds up to approximately 5%. We are, in the most literal sense, a small footnote in the inventory of what exists. And the dominant entry in that inventory is something we cannot see, cannot sample, cannot produce in a laboratory, and cannot explain from first principles. What we can do is measure its effects. And here is the thing about measuring effects without understanding causes. You can get the number right and still have no idea what you're actually looking at. Think about what dark energy does. It does not pull things together the way gravity does. It pushes space-time apart. It is the reason that distant galaxies are not just moving away from us, but accelerating away from us, receding faster as time goes on rather than slowing down the way you would expect if gravity were the only force in play. In 1998, 2 independent research teams measured this acceleration and confirmed it. They expected to find that the expansion of the universe was slowing. It was not. It was speeding up. That result won the Nobel Prize in 2011. And in the 27 years since, we have learned almost nothing about what dark energy actually is. One physicist described it as a poltergeist. We can see what it moves. We cannot see the thing moving it. Now look at what 2024 added to this. New data from large-scale galaxy surveys suggested that dark energy is not behaving as a fixed constant. The original model, called the cosmological constant, assumed that dark energy was a stable property of space itself. Same everywhere, same always. The 2024 findings challenge that directly. The data suggests dark energy has evolved over time. It appears to have become dominant around 5 billion years ago, roughly 9 billion years after the Big Bang. And its behavior since then may be changing faster than any prior model predicted. If confirmed, this is not a minor adjustment. The lead researchers described it as a potential paradigm shift, the first significant revision to our understanding of dark energy since its discovery. Here is why this matters for time specifically. Expansion stretches space-time. Not just space in the way we picture it, some empty void getting larger. Space-time, the fabric that time is woven into. When space-time expands, the geometry of the universe changes. And time, as general relativity established, is not separate from that geometry. It is part of it. Different regions of space-time experience time differently, depending on their position in a gravitational field, their velocity, their relationship to the curvature around them. If dark energy is driving the expansion of space-time, and that expansion is accelerating, and the rate of that acceleration is itself changing, then the large-scale geometry of the universe is not evolving on a fixed timeline. The timeline is part of what is evolving. What does that actually mean for time at cosmological scales? It means the rate at which the universe ages is not constant. 1 billion years measured now is not the same thing, in any physically meaningful sense, as 1 billion years measured when the universe was half its current size. The expansion rate was different. The geometry was different. Time passed through a differently shaped universe. And if dark energy continues to evolve, 1 billion years from now will be different again. We use units of time as though they are neutral containers. At cosmological scales, they are not. The container is changing shape. And here is my position on what makes this genuinely unsettling beyond the physics. We built our models of the universe, assuming we understood the dominant component of it. We had a number, 68%, and a name, dark energy, and an equation that fit the observations. What we did not have was understanding. And for 27 years, the field largely proceeded as though the name and the equation were enough. The 2024 data suggests they were not. The cosmological constant is not constant. The dominant force shaping the structure of the universe and the expansion of space-time is not behaving the way we wrote it into our models. 95% of the universe is made of things we cannot identify directly. One of them holds galaxies together. The other is pulling space-time apart at an accelerating rate that is now apparently accelerating differently than we thought. Every section of this video has examined time from a different direction: quantum mechanics, atomic clocks, the arrow of time, the behavior of photons, the variability of constants. This section sits at the largest scale, and at that scale, the news is not better. The force governing the expansion of space-time is unknown, evolving, and doing something our best models did not account for. We are riding an expansion we cannot see, driven by something we cannot identify, and the rate of that expansion, which determines in a very real sense how fast time is passing at the scale of the universe, turns out to be changing in ways our models did not predict. The global scientific community is currently in the process of redefining the second. Here is the thing about why this is happening now. The current definition of the second was established in 1967. It is based on microwave radiation emitted by cesium atoms transitioning between two specific energy states. 9,192,631,770 oscillations. That is 1 second. For decades, that definition was more than adequate. Then optical atomic clocks arrived, and adequate stopped being the right word. Optical clocks work the same way in principle. Atom transitions counted oscillations, but they operate at frequencies hundreds of thousands of times higher than microwave clocks, which means they divide time into far smaller intervals. The current record sits at 19 decimal places of accuracy. That is a 41% improvement over the previous record. The NIST clock achieving this uses a single trapped aluminium ion and a technique called quantum logic spectroscopy. It will neither gain nor lose a second over a timescale longer than the current age of the universe. The cesium definition is not wrong. It is simply no longer fine enough to capture what the new instruments are measuring. Now look at what 19 decimal places of precision actually enables. At that level of accuracy, these clocks can detect gravitational time dilation over a height difference of 1 centimeter. 1 centimeter of elevation produces a measurable difference in how fast time passes. That is not a theoretical prediction awaiting confirmation. It has been measured. It is verified. What it means practically is that optical atomic clocks have become gravity sensors. Place two of them at different elevations, and the difference in their tick rates tells you the gravitational potential difference between those locations with extraordinary precision. This is useful for geodesy, for establishing height references that do not depend on sea level, for mapping the gravitational field of the Earth in ways that satellite systems cannot match. When GPS satellites go down, whether from solar activity or deliberate interference, you need something that can hold accurate time independently. Optical clocks are that something. But here is the question those practical applications do not answer. What happens when the instrument designed to measure a thing becomes sensitive enough to reveal that the thing is stranger than the instrument was built to handle? Before you can understand why that question matters, you need to sit with what these clocks are actually probing. They are not measuring an abstract concept. They are measuring physical transitions in real atoms. The frequency of those transitions depends on the electromagnetic interaction, on the mass of the electron, on the fine structure of atomic energy levels. Those quantities are set by the fundamental constants of physics. If the constants change, even slightly, even slowly, the clocks change with them. Two clocks based on different atomic species would drift apart at a rate determined by how those constants are evolving. This is not speculation. Physicists are actively comparing different optical clock designs against each other over long periods, looking for exactly this effect. The clocks are not just telling time, they are watching the constants. What does it mean if the constants move? It means the rules of physics are not fixed. And if the rules of physics are not fixed, then the rate at which time passes is not fixed in the way the equations assume. The clocks would be simultaneously measuring time and recording changes in the framework that defines what a measurement of time even means. That is not a paradox you resolve easily. That is a foundational problem. And here is where the institutional response becomes worth examining. The papers are published. The measurements are real. The comparison experiments are underway. What you do not find is a coordinated scientific response to what the convergence of these results is pointing at. Individual research groups are doing careful, rigorous, technically precise work. What is absent is any urgency about the larger picture forming behind the data. Why is that? The professional logic of the field rewards mastery of narrow problems. It does not particularly reward stepping back and saying that the narrow problems are all symptoms of the same larger one. The redefinition of the second is scheduled. The roadmap is in progress. The technical community is handling it as an engineering and metrology problem. That framing is not wrong. It is also incomplete. Because the reason the old definition is no longer adequate is not simply that the clocks got better. It is that the clocks got precise enough to reveal things about time that the theory behind the definition did not anticipate and still has not fully absorbed. The clocks have gotten precise enough to show us something that the theory does not yet have the vocabulary to describe. Here is what you have if you put all of this in the same room. Clocks that tick at different rates depending on altitude. Photons that spend negative time inside matter. A quantum system where the mathematics of time remains reversible in both directions. Constants that may not be constant. Dark energy accelerating the expansion of spacetime in ways that do not match the models. And instruments now precise enough to detect effects that no existing theory fully explains. That is not one anomaly. That is a pattern across every scale of physical reality we have examined. Here is my position on that. When multiple independent fields of physics converge on the same structural problem from different directions, the honest response is not to treat each finding in isolation. The honest response is to ask what they have in common. And what they have in common is this. Every one of these results is incompatible with the assumption that time is a fixed, smooth, universal backdrop that everything else happens against. That assumption is not a law. It is a convenience. And the data is telling us it was never quite right. Now look at what the institutions are actually doing with this. The papers are rigorous. The methods are careful. The journals are credentialed. What is missing is any urgency about what the convergence implies. Individual findings get published, covered, and then treated as specialized results for specialists. Nobody convenes a serious cross-field effort to ask what it means that quantum mechanics, general relativity, atomic clock measurements, and cosmological observations are all producing results that strain the same foundational assumptions simultaneously. The silence is not because the question is trivial, it is because the question is too large. Why is that? Here is the thing about institutional science. It is built to advance incrementally. A physicist working on quantum collapse is not incentivized to spend time connecting their results to what a cosmologist found about dark energy last year. The fields do not talk across those distances often, and when the implication requires admitting that something foundational may be wrong, the professional incentive is to be cautious, precise, and narrow. Broad claims are where careers go wrong. Narrow findings are where careers are built. So the pattern sits in the published literature, distributed across dozens of subfields, and nobody's job is to stand up and say what the whole picture looks like. What does the whole picture look like? Time is local. We have measured that. Time may have quantum properties. The research points that way. The direction of time may be emergent rather than fundamental. The mathematics support it. The constants that define how time behaves may be slowly changing. The evidence is not settled, but it is not dismissible either. The dark energy driving the expansion of spacetime is evolving in ways we did not predict, which means the rate of that expansion and what it means for time at cosmological scales is not what we thought it was. These are not fringe positions. They are published findings in mainstream physics. What they add up to is a picture of time that is nothing like the picture most people carry. Not a smooth river flowing in one direction at the same rate everywhere. Something more local, more variable, more subject to the physical conditions around it than any intuitive model suggests. And we are early in understanding what that actually means. The tools have outrun the theory. The measurements are telling us things the framework was not built to receive. The evidence is not that time is broken. It is that our picture of what time is was always incomplete, and the instruments we built to measure it have finally gotten precise enough to show us the edges of what we got wrong.